Hey guys, let's talk about problems 18, 21, and 25 in Achieve section 4.2. The first two problems deal with the extreme value theorem, and the last one is going to deal with Rolle's theorem. Remember, the extreme value theorem is just saying that the maximum or minimum value of any function on a closed interval is either at the endpoints or at any critical point within those endpoints. So the critical points are where the derivative either doesn't exist or is equal to zero. So I had to take the derivative of my function. I used the quotient rule. The denominator times the derivative of the numerator minus the numerator times the derivative of the denominator over the denominator squared. Then I just algebraically FOILed out my second group, and I knew I was subtracting that entire second group. So then when I did that, I had x squared minus 2x squared is a negative x squared. 3x minus x is 2x. And then I had a minus a negative 3 for plus 3. So now I have my simplified derivative. I know that the only value that this derivative wouldn't exist at would be a value that makes the denominator 0. That's not important because it's not a point in the original function, since this denominator is the same as the original function's denominator anyway. So I can say, well, it's the same as the original function's denominator squared. It has the same restricted values. So I would say the only critical points we're going to get is by setting this fraction equal to 0. And please remember, the only way a fraction can equal 0 is if the numerator is equal to 0. The denominator never makes a fraction equal to 0. So what I did here to solve for the critical point is I just said, let's set this numerator equal to 0. Now, you'll also see what I did in this step. To make it easier to set equal to 0, I went ahead and multiplied it by negative 1. So that's a legitimate maneuver. You could say, well, algebraically, you just multiplied both sides by a negative 1. So then the quadratic becomes positive x squared minus 2x minus 3. And I still have that equal to 0. Now this factors really nicely, factors of negative 3 that sum to get to negative 2. I can say x minus 3 and x plus 1. Now when you set these factors equal to 0, you get an x equals 3 and an x equals negative 1. I'm not concerned about the negative 1. Now, when I say it's not in the domain, it's in the domain of the original problem. It's just not in the domain of this specific extreme value theorem from the problem. So it's not in the domain of interest of this problem. I only need to be worried about the 3. So I take my two endpoints and my critical point within them 3, and I just test what this function is at each of these values. Now, it's very easy to plug in here. When you plug a 1 into it, clearly you see your numerator 0, so your fraction 0. When you plug a 3 in, your numerator is a 2. Your denominator would be 3 squared plus 3 times 3. That's going to be 18. 2 over 18 reduces down to 1 over 9. When you plug the 7 in, your numerator is going to be a 6. Your denominator is going to be 7 squared plus 21. That gives us a 70 down there. I just said 6 over 70 reduces down to 3/35. Now, 1 over 9 is going to be slightly larger than 3/35, so that's going to end up being my maximum value, and clearly I have a minimum of 0. Now, the values that they want on Achieve are the y values here. So when I go to check this in, and I need to make sure I go to the correct problem on Achieve. I'm looking at number 18 right now, not number 25. So in number 18, it asked me to do this problem that I've been discussing with you. And it's saying the minimum, well, the minimum of this problem is at 0. The maximum of this problem is at 1 over 9. I'll put that in. And then I can check answer, and it should say correct. Now, for the next problem, that was 18. The next problem in question was 21 that I want to look at with you. So in 21, I'll raise this up here to look at that problem. Again, it's an extreme value theorem where we're looking at this original function. Now it's the interval 0 to pi over 2. And the extreme value theorem says that any maximum or minimum on this closed interval is going to occur at the endpoints or at any critical point within. So I had to take the derivative. I know that the derivative will always exist because the derivative of sine and cosine always exists. So when I take the derivative here, I had to use the product rule. I said, well, I have the product of 10 sine x times the cosine function. Well, the derivative of 10 times the sine is 10 times the cosine. So that's derivative of the first times the second cosine plus the first 10 sine x times the derivative of cosine, which is negative sine. Now, of course, the derivative of the constant canceled out and gave me a 0. So here's the derivative of my function. I needed to go ahead and simplify that. I saw I could easily factor out a 10, and then my first term would be cosine squared, my second term would be minus sine squared. So I had 10 times cosine squared minus sine squared is equal to 0. If I try to find the critical point, it's just going to be when cosine squared minus sine squared is equal to 0. That's going to occur whenever cosine squared x is equal to sine squared x, and that should be pretty easy to think about. If you're thinking on the unit circle, when can you square the cosine function and it equal the square of the sine function? Well, you know, at every midpoint of every quadrant, the sine and cosine are, at pi over 4, they're both the positive square root of 2 over 2. But even at 3 pi over 4, the only thing that they differ by is in their sign. One, the cosine's the negative the square root of 2 over 2, the sine's the positive square root of 2 over 2. But if you square both of those, they're the exact same. So I say, well, it's at every mid-quadrantal angle, pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Now, unfortunately, in this problem, I only needed one of those critical points because the interval I was interested in is 0 to pi over 2, so I said only pi over 4 is in the domain of interest. So I come over here, extreme value theorem, evaluate your function at the endpoints and at the critical point within those endpoints. I did that over here, and I know that as soon as I plug in a 0 or a pi over 2, this first part's going to give me 0. The sign of 0 is 0, 0 times any number is 0, so I just have 0 plus 8 there. Same thing happens here because the cosine of pi over 2 is 0. So I have 10 times the sine of pi over 2 times the cosine, which is 0 plus 8. So I get an 8 either way there. In the middle portion, when I evaluate at pi over 4, I'll have 10 times the sine of pi over 4 times the cosine of pi over 4. Both of those, as we just discussed a minute earlier, are both the square root of 2 over 2. I know the square root of 2 over 2 times the square root of 2 over 2, that's just going to equal 2 over 4, same thing as 1/2. I have 10 times 1/2 is 5, plus 8, I get a maximum of 13. Now I should be able to go back to my problem on achieve and say, well, for the minimum, it better be 8, and the maximum should be 13. I'll check that here, and they say yes. Now, the last one, I really like this one, the problem dealing with Rolle's theorem. So with Rolle's theorem, I need you to remember, Rolle's theorem just stipulates that if a function begins and ends at the same point, then you know that the derivative has to be 0 for some x value in between those two endpoints. So here, it's asking us to consider Rolle's theorem for the interval 1/2 to 6. Well, I just verified real quickly that Rolle's theorem should apply. So I plugged in the 1/2, and you see when I did that, I got a 1/2 plus 3 times 1/2 to the negative 1 power. That's just 2. If you take the reciprocal of 1/2, and I have 1/2 plus 6, that's 6.5. Okay, now f of 6, find the other endpoint in the problem. Well, when I do that, I'll get 6 plus 3 times 6 to the negative 1, that means 3 over 6. Well, again, that's going to be 6 plus 1/2, 6.5. So I get the exact same y value no matter which endpoint. So that means this function begins and ends at the same point. If that's the case, the derivative has to be 0 for some x value that we call c in between 1/2 and 6. So I take the derivative. The derivative of x plus 3x to the negative 1 was 1. And then, of course, I had to bring the negative 1 down to get the minus 3x to the negative 2. That's better written as 1 minus 3 over x squared. I set this equal to 0 because I know, again, my derivative has to be 0 for some x value in between 1/2 and 6, according to Rolle's theorem. So I try to find that value. When I do that, I move the 3 over x squared to the right. Then I just multiplied both sides of my equation by x squared, and I get x squared is equal to 3. Then you can say, well, you can solve for x by saying now x is the positive or negative square root of 3. Now, the only one of those answers that's within our interval, and we knew there had to be at least one answer between 1/2 and 6 that satisfied this criteria. Well, there is. The only answer that's in that region is the root of 3. So we'd say the value of x equals c that satisfies Rolle's theorem such that the derivative is equal to 0 is our value of c is the square root of 3. Now let's check that out here. If I say square root of 3 and we check, and it should say correct. Okay, guys, hope this helped out with these 3 problems. They were pretty good ones. I really liked them, especially that Rolle's theorem problem. Let me know if you have any other questions. I'll be glad to help.